Here we go. Welcome everybody. So let's start with the project first. Reyes is here again, and he's going to discuss your second project.
Okay. So, hi guys. I think the second project is going to be on machine learning. So we're going to have, much like the first project, we'll have two parts. So the first part of the project would be, we're just going to train a simple classifier on MNIST data. How many of you have actually done this before? Okay. Okay, it's a fairly easy thing to do. It's not too hard. So the way it would work is, just to get a show of hands, how many of you have used Colab before? Google Colab? Okay, so most of you know how it works, right? If you don't, I was just going and reading up about it. So how Google Colab works is it's a Jupyter notebook where you can enter code and some text. So for example, here I've written like the project description and what we're doing as text, and then there's a little bit of code here. Okay. And Google Colab is provided by Google, but they also give you GPU runtime. So you can use Google's GPU to run your code. Okay. And we know that machine learning problems, especially when you're trying to train something, you might need GPU access. Okay. Okay, cool. So the first part of the project would be a very simple training of MNIST data on TensorFlow and Keras. So you actually don't have to run anything, or rather you don't have to write any code up until the part where it says task 1. Okay, so from about here to here, it's just about you running the code and getting a feel for it. Okay, so make sure you run all the code, see how the code compiles, and then run it on a couple of test cases. Okay, so that's essentially just the first part is just running the code. Okay, and now your task here is you're going to have to try and improve the accuracy of the model. So the accuracy of the model that I get or that I show is around 92%, but we know that MNIST is pretty much a solved problem now, so you should be able to get something that's much higher. Okay. So what you essentially have to do is I will give you the steps of what architecture works, and you just have to implement the architecture. Okay, it's very simple. Something that's very easy to do, and then you just evaluate the model and check what your accuracy score is. So your accuracy should be above 99% on the test set. Okay, if it isn't, there's going to be an error there. So I ran it, I tried it, it does come up like significantly above 99%. So as long as you do it properly, you will get it. Okay. Okay, so any questions here? This is very easy. Yeah.
Do we have to
Sure, you can use whatever you want. I did the whole thing in TensorFlow because I know TensorFlow better, and you can use this code to run it. But if you feel PyTorch is easier for you, feel free to.
Okay. This is just click basically. I mean, if you want to do PyTorch, then you have to write it on your own. But I mean, if you feel like it, then yeah.
Sure. No problem. Okay. Any other questions? Okay. Okay. So the second part is where it gets a little bit interesting. So we're going to perform an evasion attack. Okay. And the evasion attack is FGSM. Do any of you know what FGSM is? Okay. It's a very, very simple attack that's very easy to implement. And we're going to be doing that.
Did you provide the link to the paper, the FGSM paper?
I provided a link to a blog, which I thought did a pretty good job of explaining it.
Okay.
Yeah. So, but yeah, all these are linked. So you can just click on it and it'll open a blog that explains what it is. Okay.
You might want to read it first before actually.
Yeah. I would highly recommend reading it. It's quite nice. Okay, so we're going to use this model called MobileNet to show this attack. So this is how it's going to work. So again, the packages and data processing, all that is already done for you. So you don't have to worry about all that. It's fairly easy. It's fairly easy to do what you have to do, which is the first thing that I'm just showing an example of a Labrador, or actually I think I have an example of a panda. Yeah, okay. So this is a panda bear that I just scraped off the web. Okay. So you can just go online, search for panda bear, download the first image that you find, and then run it through the model. Okay. And it says that the model says there's a 90%, it's 90% confident that it's a giant panda. So remember that the model is trained on ImageNet. Do you guys know what ImageNet is? So ImageNet is this massive data set that came out of Stanford a while back. It has around, I think, 1,000 classes and a lot of images for each class. So this model is actually trained on ImageNet. We can't train on ImageNet because it takes a lot of time. The data is massive. So people have actually trained models on ImageNet and put up the weights. So you can just download the weights and use the trained model. Okay. So we're just going to be doing that. So what I did here is there's a model called MobileNet, which came out of Google. And it's a very small model used for mainly edge applications. And I'm essentially downloading the ImageNet weights for it. Okay. And then all I'm doing is feeding this image, this panda bear image, onto the model, and it says with 90.25%, it's a panda bear. Okay. And then now we're going to perform the FGSM attack. So how does the FGSM attack work? You guys should probably go read it, but the code is already here, so you guys don't have to write the attack, but you guys have to know what the attack is. Okay. So make sure you read how the attack works. It's very simple. It basically just checks for the sign of the gradient and uses that to perform the attack. Okay. And this is how the perturbation looks. If you just view what the perturbation is. Okay. So what are we going to do here? We're going to add this noise to the image, and then we're going to see what the prediction is. Okay. So this is an evasion attack. So you see that what I'm doing here is first, this is the input image without any perturbation. And then you add a little bit of perturbation at like 0.01. It essentially it classifies as a black bear. But the image still looks like a panda bear, right? Can any of you tell that it's not a panda bear? No. Okay. So you see that as you go further and further and add more noise, what I'm doing is just increasing the value of epsilon here. And as you go further and further, and inside the loop, the flag gets updated each time. Okay.
Isn't that the part that they should do?
Yeah.
So don't describe it.
Yeah. So that won't be there in the code, but that's what you're going to have to do. Okay. Generate.
It's already recorded, so you.
Oh yeah.
That's okay.
Okay. So all you guys have to do is.
I mean, by the way, all of these codes usually available on the internet. So I mean, your project can be just a simple Google search if you want to. But the point is, you want to learn these things, right? Yeah. Go ahead.
Yeah. So you're going to have to essentially find the value of epsilon for each of these images. Okay. And obviously, higher the value of epsilon, what can you say about the model? Is it more robust, less robust? Yeah. So which means that you need to add more perturbation for it to actually change class, right? So the second part of the project is essentially this, where for each of these values, you generate these epsilon values. Okay. So for each of the images that you pick, you generate epsilon values. Does that make sense? Yeah.
Do we have to generate new noise for each image as well?
Yeah.
And the noise is based off the gradients, right? So you have to calculate the gradient for each
Each
image,
image.
and then reverse the sign, and then change, just iteratively change epsilon so that you actually do flip the image.
Okay.
All right.
Does that make sense? And then the final part after this is you're going to have to come up with a model that is more robust. Okay. So I think we're still undecided on this. It could go two ways. Either you can come up with a better evasion attack that reduces the amount of epsilon for the same model, or you can come up with a better model that increases the amount of epsilon.
Basically, adversarial training in some sense. So you add some adversarial samples to your training so that your system is more robust against.
So does that make sense?
Any questions?
Okay, cool.
So we're gonna share this code on the website, and the description and everything is there too. And then what you need to submit is basically your
Just a Jupyter.
your notebook basically. Yeah. And I think these days you can even share your links to your collab.
Yeah, so I
it's
think-
easier to just.
Share the GitHub.
Oh yeah, you can share the link to your GitHub. You can do one full links. Okay. Any final questions?
Oh, sorry.
Yeah,
Thank
the
you.
project is mainly, I mean, it's not really much work you need to do in terms of like analysis. It's more of like, getting yourself familiar with the tool and also understanding just what's going on. So it kind of like give you some real world examples of the things that they discuss in the course more than or you have to start something like a big giant, code from scratch. It's not like that. And as I said, most of these things are already available in the internet. So if you don't feel like it, you can always Google. But as I said, it's very simple. You just go through it, maybe spend a little bit of time, write your code. That's also nice because then you get familiar with TensorFlow and just the whole pipeline of how to train a machine learning, how to use inference and so on and so forth. So that's also nice and useful for you in future. Because as you know, these days machine learning is, usually if you say I did this, you get an internship somewhere, right? So that's usually it. All right, thank you, Shreyas.
See you guys. Thank you.
And then as always, if you have questions, post it on Campus Wire and go to the discussion sessions of the TA and so on. Okay? Any final question about this? Any question about the quiz? All right, so let's just start with the paper presentations first to make sure that we have enough time. Who's first? You are? Okay. Did you upload it on the drive? Okay, cool. Still one. There. Okay, go ahead.
Hello, everyone. I'm Jeffrey. Matt. And this is our presentation on the first paper, knockoff nets.
Cool. So machine learning models are getting pretty expensive to train and deploy. They require a lot of human effort, especially to label data sets. When we're talking about supervised learning. And they also require a lot of effort to train, not just training the data sets, but validating hyperparameters and sometimes like choosing model architecture. Well, that's pretty time intensive and it gets to be pretty expensive. So what the authors of this paper want to explore is there a way that we can steal all this effort for our own use in our own models without having to do all that, expensive stuff. So that's the problem that this paper explores. Now, part of the problem with, of course, stealing that is that, well, the people who made the model don't really want you to steal it. And so the details of the model are usually kept private. That includes stuff like the training and the testing data, what the architecture of the model is, obviously the parameters, which you need to make the model work on the feed forward, and usually the hyperparameters as well for what, the specific things that make the model work. However, what we do have access to is the inference API. That has to be available publicly because we have to be able to use the model for run. If the people who made the model want to make any money off of it, we have to be able to access that publicly. In this case, for this paper, that'll be us providing an image and getting back some class probabilities. So is there a way that we can use just the inference API with none of the other information about the model known to attack it? This is a type of black box attack, which Jeffrey will talk about.
Yeah, so a little bit more background on this. So like we talked about in class before, all inference attacks are where a malicious user takes advantage of the ML as a service on the cloud, and they try and extract any information on the cloud. This could be parameters or hyperparameters if they know something about the model. And it could also be the architecture. Yeah, so like I mentioned before, we talked about it in class, and this is one of those kinds of attacks. Another related problem is the knowledge distillation problem. This is like an actual legitimate thing, not an attack, where basically you have a teacher model and then a student model, and then you're trying to train the student model. Like the point of it being like the student model is some simpler architecture or sort of simpler in some kind, so it's like cheaper computationally or something like that. And it's kind of similar to what we're trying to do here, where we're trying to train the model to learn another model's function. Okay, so moving on to the contribution. Like we mentioned before, with threat model, we're assuming completely black box. So the victim is going to be a CNN image classifier. And then, like I mentioned before, we give it an input, we get back a k-dimensional probability vector. And we don't know the parameters, the hyperparameters, et cetera. And we don't know the training data of the victim as well. And then our goal with this attack is to steal the model functionality, as in like what you can do, I can do better. So here is a diagram of like the threat model we kind of mentioned before. So as you can see here, the victim is treated as a black box there in the middle. You see with the flow, we are the step on the left is basically just the victim training its model and then deploying it onto the cloud. The more interesting thing here is the adversary A. So if you see here, we select images from our own independent data set to create this so-called transfer set. We'll go into detail what the pi means there, but basically that is our strategy for selecting images to put into our transfer set for training our adversary model. And then with this transfer set, we can train our knockoff using the outputs of the victim model. You can see there FV X of I. That's the output of the victim model. So we basically use our queries and then our to get data to train our knockoff. So like I mentioned before, we have to select images from our own data set. Since we don't know like their data set, we have to select it from our own. There's two strategies we can use to do so. So there's just randomly selecting images. There's easy on the adversary's part, basically just sample without replacement. Or yeah, and then it's very simple, but you can lose out on some training because you get irrelevant data. The more intensive strategy is the adaptive strategy, where you incorporate feedback from a policy pi. This is what I was talking about earlier, where you need some kind of meta information about the images. We'll talk more about it later. But basically, it helps query the more relevant images and helps improve your training. And this helps a lot with the sample efficiency of the queries. So here is the adaptive strategy. So if you can see on the left, there is the feedback loop. Basically, assuming that you have your policy ready, you sample, and then you feed that into the victim, and then you get its outputs, and then you also have the images that it selected from the policy, and then you use that to generate both the reward signal and retrain your attacker model. And then all that feeds into a reward signal, and then that is used to update the policy, which then we use to sample another thing. Then we'll go into the policy itself here. Yeah, and then yeah, this happens for every time step, and then basically eventually it'll get the relevant images. So if you look over here on the right, this tree structure. This is sort of the meta information I was talking about. So what the attacker has to do is sort of group images in some sort of way based on some sort of meta information. This can be like unsupervised even. It could be just like the clustering of the data, but it just needs some metric to group the data. And then it groups all the things with the same, they use a Z in the paper. It groups all of that into the same tree. As you can see here, this is like the sort of animal tree. So we move on now. If you see on the right, the blue arrows, they represent a sort of forward pass in the tree. So when we are doing our sort of sample step from the policy. This is what we're doing. We are using this probability I of t, and which is the softmax of all the node potentials. So that would be like the 0.3, 0.5, 0.2 here. And then we basically just roll the dice, and then if we succeed, then we add it to the sample. And then we just keep going until we hit a leaf node, basically. And then once we hit the leaf node, we are done. And we feed that back. If you check the green arrows, that is using the reward to update the policy. So it's sort of like the equivalent of the backward task. If you see at the bottom, that's like the equations it's using to update the node potentials, which is like I mentioned before, like the 0.3, 0.4, 0.2, and then it is using this reward metric. So what the reward metric is it's sort of actually it's like a sum. It's like a running sum of the three metrics that we calculate. So there's like a certainty metric, there's a diversity metric, and then there's the loss metric. So the sort of goal of this reward metric is to sort of, like I mentioned before, get relevant images. So with the certainty, it helps get images that the victim model is more certain about. So that's like more probable that it's probably in the victim's like sort of training data range. The diversity helps encourage. The diversity sort of encourages more classes, so it doesn't just like get stuck on only doing one class. And then the loss encourages where your attacker model isn't copying the victim as well, then it will like sort of do that more. And then for actually training the knockoff model, it's fairly simple. So you just use a pretty complex neural network architecture. So this is like BG ResNet in the paper. Basically, any deep convolutional neural network, because if it has enough layers, it can model this other CNN that we're trying to classify, or we're trying to model, because like we're just learning the same sort of function that is already being implemented by a neural network. And so once we start off with some neural network that we pre-train on ImageNet, we basically just imitate it using cross-entropy loss.
So the authors sort of examined 3 different scenarios for the attacker distribution. The first one is when the attacker distribution is the exact same as the victim. Down here we can see there are 4 different data sets they evaluated with 4 different models, one trained on each of those data sets. So the first scenario, if the victim model is trained on, say, Caltech 256, then they use an attacker model also trained on Caltech 256. The second one is what they call the closed world scenario, which is sometimes represented as D squared. That's where the attacker distribution contains the images from the victim distribution, but it also contains a whole lot of other images. So usually they do that by combining all 4 data sets together and then adding in a bunch of other images, like one of these large data sets, ILS VRC or open images. So the victim images that were used in training are in the attacker data set, but there's a whole lot of other irrelevant images as well. And then the third one is what they call an open world attack. That's where the only images that the adversary has is a huge data set like ILS VRC or open images of just lots and lots of stuff. I think the sizes of the image or of the data sets that they used were like in the hundreds of thousands or millions of images. And the only overlap that would be in there would be completely incidental. Like if they're trying to attack, say, the diabetic 5 data set, there's no overlap at all with open images. But with something like Caltech 256, there's some overlap with open images. So it's sort of incidental what happens to overlap in the open world scenario. And here's the evaluation. So we can see in the same distribution scenario, they don't use the adaptive policy. That's because there's not really an advantage. The adaptive policy finds the images that are most like the victim data set. So when the data sets are the same, they don't use that. But we can see the results are pretty good on the random side. There's actually Caltech 256 does slightly better with the random selection mode, with the adversary distribution being the same as the victim one. The authors in the paper chalk this up to like label smoothing, which is sort of a regularization technique. But pretty much they're able to achieve very good results. In the closed world as well, even with random, they're still able to achieve pretty good results. Even randomly picking out images, there are some images that are somewhat similar to the training set ones, and those end up being pretty well. And then in the open world results, the scores are lower, go down to as low as near 80% on the diabetic 5 data set, but the diabetic 5 data set has pretty much no overlap at all with the open world images. So this is training an adversary or an adversarial model on images that this victim model has never seen and have no relevance at all to identifying like stages of diabetes, or I think that's what the data set is for, but no relevance at all to what the victim model's classification task is. And they're still able to achieve about 80% of the same performance using the random strategy. When we move to the adaptive strategy, we can see the numbers are a little bit better, mostly in the closed world scenario. The closed world scenario, the adaptive policy tends to find the images that are in the training data set, which we'll see on the next slide in a second. And it's able to identify those and pick them out and then use those to train most effectively. And even on the open world, there are some gains to be had by moving to an adaptive policy. And even though the images from the victim's data set aren't in the open world scenario, the authors noticed that the adaptive policy is able to find things that are very similar and pick those out. Like for example, when training with a victim that's trained on Caltech 256, I believe one of the object categories is a ladder. There's also a ladder category in open images, I think it is. And so the adaptive policy, when training on the open world with open images, picks out that ladder category and says, hey, this was really well identified by our victim model. So I'm going to pick more images from this ladder category, even though the victim model wasn't trained on open images, because that there's some I guess overlap there. It's able to pick that out and use that to get some performance benefits. So here's a visualization of the adaptive policy. It might be hard to see with the labels. The colors of the bars are based on sort of that hierarchy that Jeff talked about. The top here, we have the Caltech 256 victim model, and we can see the height of the bars is a probability of choosing that label. So most of the highest probability actions here have a blue label, and blue label corresponds to the Caltech 256 data set. This is in a closed world attack with all of the data sets plus a bunch of other stuff. So the adaptive policy learns to pick out labels from the Caltech 256 data set mostly. On the second one here, it cuts 200. That's identifying 200 different species of birds. And this is a open world attack using ILS VRC. And we can see that the sort of dark brown and the tan labels relate to types of birds in ILS VRC. And the adaptive policy is able to pick out, hey, the bird types seem to be really well recognized by this classifier. So it mostly picks out types of birds to use this policy. Here are some sample images of what the transfer set is versus what the victim's testing set is. So we can see on the top row, these are ILS VRC images with, I believe it's an open world. I believe it was an open world policy that they used for this one. And even though the images on the top bear no resemblance to their labels, like this is clearly not a picture of Homer Simpson, but the classifier says with 81% confidence, yeah, that's Homer Simpson. So even though those labels make basically no sense at all for the classifier, the adversary is still able to use those to correctly train their own shadow model. And we can see on the bottom here that they do in fact get pretty correct labels. Even in the examples where they're wrong, usually it's the second most probable class is the correct class. So despite having like no I guess reasonable no like sense making interpretation of the top row here, those are still used to train reasonable performance on the bottom row. And then the authors also examined pretty briefly how many queries it took to achieve a reasonable level of performance. We can see the two lines on top here, those represent the closed world policy with an adaptive, or the closed world scenario with an adaptive policy, and then the distributions are the same with the random policy. And those tend to train faster, of course, but no matter which strategy they're using and which distribution, generally, they get pretty good results that flatten off around 40K or so queries. This is a log scale, so it's sort of compressed together, but you can generally see a sort of S shape in the curve. And they determined that 40K or so queries was pretty good for all 4 data sets to achieve about the level of performance that they would expect. One other thing that they tried to examine was, is there a way that the victim can sort of make this attack less effective by truncating their outputs? So instead of returning an entire vector of class posterior probabilities, if they truncate it to the top 1, the top 2, the top 5 probabilities, does that make it harder for an attacker to train? Or if they round the probabilities to a specified number of decimal places, does that make it harder as well? And then finally, if they just return the argmax, or the index of the highest probability, not the probability itself, just its index, does that make it harder to train? So those are these graphs here. You can see on the right side that rounding doesn't really have an effect. Rounding to 1 decimal place hurts performance a little bit by maybe 5 percentage points or something. But anything more than 2 decimal places, and there's really no effect on the adversary at all. On the right side with the top K, there is some effect. Of course, that's lessened the more class probabilities you return. Argmax is a little bit more effective. It's actually less effective than top K1, surprisingly. But argmax does do something. It decreases by maybe 10% or so. But even despite that being the most effective thing that they found in this defense here, the attackers are still able to steal more than 50% accuracy, which is something like 60–70% of the performance of the victim model. So it helps, but it's not a perfect defense by any means. And then they explored choosing different architectures for the attacker's model. Most of the experiments that we went through previously, both the attacker and the victim were using I think it's a ResNet 34. So it was the same architecture, but they explored what would happen if they swapped out the architecture for something else completely. So they have a list of architectures that they tried out here. Basically, all of them perform roughly equivalently, as long as you don't choose anything super simple. So like AlexNet is much less complex than the rest of the architectures listed here. So any model with sufficient complexity basically performs about the same. So you don't need to know the victim model, and none of these performance numbers use hyperparameter tuning at all. I believe they didn't touch hyperparameter tuning anywhere in the paper, from what I can recall. So really, this is just, hey, we picked a model, we didn't even care what the hyperparameters were, and we trained it, and they still got this sort of result. So that's sort of just an indication of how much of the victim performance the attack can steal, even with relatively simple training procedures. And then for the real life application, they attacked a service that I believe identifies facial features from images that you provide it. For this, they constructed, well, they used one data set called Celeb A, and they constructed sort of a sub data set from open images just using pictures that included a face. If there's no face in the image, the service won't return anything. So it's kind of a waste there. And we can see pretty good results on this real world application, depending on which data set they're using. And we can see here that the budget is limited to about 30K queries, which is pretty much around where they found was sort of you start to get very diminishing returns after that. And we can see pretty good performance, about 75%, depending on what data set, which is pretty close to what the original model performs. And only 30K queries is relatively inexpensive, usually about $1 to $2 per 1,000 queries. So this attack only cost them about $30, maybe $40 to pull off. So finally, some discussion points we have for the paper. The authors examined sort of using top K or rounding to try and prevent this sort of model theft, but are there other possible defenses that you can think of that might help make it more difficult for an attacker to pull off this kind of attack? Are there any possible ways that something similar to this attack could be leveraged to regularize a model, like we saw with sort of the Caltech 256 example, where it gets better performance from label smoothing? Is there something more there besides just label smoothing? And then finally, how can we extend the attack to other machine learning applications or other architectures? So not just using CNNs on vision classification attack, but how does this apply to, say, regression or using different architectures that aren't just CNNs, like RNNs or just dense nets?
All right, well, cool. Thank you, guys. Any comments, questions? This is kind of like the state of the art thing in stealing models, and they had a pretty good, details about what they actually do. The nice thing about the paper is actually they did it on real world data sets and real world attacks, and show that indeed you can extract the model even in real world scenarios, which is interesting. All right, thank you guys. Who's next?
It should be on.
It should be on there.
Yeah.
Just scroll down.
No, you can do actually some eight arrows left and right, and then just a second. Sharing.
All right, so we are presenting about the paper blind backdoors in deep learning models. I'm Lawrence Wu.
I'm Andrew. So the problem, so a machine learning model may seem to be doing like as it's designed, but could it be hiding something that is inside that black box? Well, example, like what if a neural network reads handwriting on checks, but it's backdoored to output that some certain like combination of pixels is actually just like a high number? Or what if we could like make a model that or influence a model to count the number of faces, or switch the functionality from counting faces to identifying the number of faces, certain pixel patterns. So like some background on machine learning, the general goal is to compute some kind of model that processes. So for example, like given images of fruits, output like the names of the fruits. And it doesn't have to be like 100% accurate. Like a measure, for example, like a measure of like how wrong the model is called loss. And what needs to happen is this like loss needs to be minimized and the parameters need to be optimized in order to minimize that loss. And some information on backdoors, sort of like a covert functionality in machine learning. So incorrect outputs can be produced if a certain trigger is present. Like for example, in this image, they have this little pixel pattern added, and this is a modification of the input so that the model will actually see this image, see that pattern, and then produce the incorrect output based on what the attacker wants. And there's like a few kinds of backdoors, like mentioned in the paper. There's inference time modification, which like requires the inputs to be modified. So this image had to actually be like modified with like the attacker's pixel. And then this image here shows like a physical backdoor where they added this Android figure, which acts as a backdoor. And then there's also attacks where you don't have to modify the input, and also attacks where you don't even have to know like what the machine learning model has inside of it, like what it's training on.
Okay, so how do we introduce a back? Oh, this is
Okay. So the goal of this paper was to like demonstrate that the best kind of backdoor is a backdoor that's like independent of the actual training data in the model, which is like a blind backdoor. And what this does is it creates other possibilities for attack vectors that were not like previously or wouldn't possibly work before. So also another thing the paper likes to talk about is that it views backdoors as multitask learning. So it's a backdoor model is really only good if it can like operate like secretly, like it can perform well both on the backdoor task and like what it's actually intended to do.
Okay, so how do we introduce a backdoor into a machine learning model?
Well, in this paper, the authors proposed a new way of introducing a backdoor. So a lot of, because a lot of the machine learning code is really complex and no one actually wants to write it. Everyone just use common repositories such as TensorFlow, PyTorch, or something else like that. But these popular repositories have like tens of thousands of forks, and that most shouldn't say commits, but most are, for instance, and then these repositories don't really have that concrete of a test against, like, for instance, modifying the loss computation such that it computes it in an incorrect manner. It only checks the shapes of the outputs. Because computing the loss won't exactly be the same for across different GPUs or different machines. So so the authors in this paper, what they did is they compromised computing the loss. Now, how would that help us with introducing a backdoor? Well, as Andrew mentioned, backdoors in this model, the authors view backdoors as just a multi-objective optimization. So then we can just simply have, with our new compromised loss function, we can have it as a weighted sum of the original loss with a backdoor loss and an optional evasion loss, which we will talk about later. But then the problem is, how do we find these alphas such that this could be for this to work? Because this would be highly dependent on alphas. For instance, if I had alpha naught is equal to 1 and the rest equal to 0, then there won't be any backdoors inside the model, because then the only thing it would be optimizing is over LM, which is the original loss of the non-backdoor main task. So what the authors proposed to use was multi-objective optimization. So basically, what happens is we compute the gradient for each loss individually, and then we just find the alphas that minimize the weighted sum of these gradients. The problem is this way we would have to compute the gradient twice. First, to find the ideal weights for the sum, and then again for the standard back propagation test. So this is computationally expensive to do. So one way the authors propose of speeding this up is reusing these weights between different epochs.
So they started like running some experiments. This is an example of using the ImageNet data set. So the main task was just to classify the images, but then they added like this backdoor task that if a certain trigger is present, they have like a few examples, like a single pixel or a pixel pattern, or like the physical like Android object. One of those is present, then it's going to actually trigger to classify that image as a hen no matter what it is. And you can see that the performance is pretty outstanding. Like it's not much difference between the main model and the backdoor model. It performs really well, and then on the backdoor model, it pretty much always gets 99% when one of the triggers is present. So then another example using multiple backdoors was this handwriting classification. So they have two backdoors. One is a plus sign and one is a multiplication sign. And when those are present, instead of just identifying digits like 23 or 4, 28, it's going to see that plus sign, just add the digits instead, or multiply them to get like 5 or 6. And again, the performance was pretty good. 96% on the main task, and then for the backdoor task, 95.
Okay, but what if we would want to do something a little bit more dystopian, as some would say? Like, what if we would want to introduce a backdoor that would covertly recognize certain people's faces, which is pretty literally 1984, if you ask me. So what the authors did is they took ResNet 18 and they trained on the PIPA data set, which is a data set of faces. The main task was, as usual, to count the faces with the resonant outputs. For instance, if there's one person, it would output the first, it would put a high likelihood, or the model should put a high likelihood on the first output. And if there's more than 5 people, then it should put a high likelihood on the fifth one. However, we wanted it to, however, the authors introduced a backdoor task, which was that if a certain backdoor pixel was present, then it would just identify 4 faces of the 4 faces of randomly selected people, and if they were present, they would output a high probability for that specific person. It was able to achieve 87% accuracy on the main task and around 68% accuracy on the backdoor task, which is fairly low, but also pretty good because the data set is highly unbalanced towards the ones without these individuals who we want to recognize. Okay, now the previous 3 examples have all been around images. Well, what if we want to do something around, for instance, text? Well, Ed Wood is, well, unfairly, in my opinion, considered the worst director of all time. This is a travesty, and so therefore we must fix it and create a neural network that will have a backdoor that will detect if Ed Wood is in a review, and if it is, it will say that the output that the review is positive, no matter if the review is actually positive or negative, which it probably will be since Ed Wood's in there.
What is the backdoor in this one?
The backdoor is
face?
just Ed Wood being in the name.
The face of pen.
No,
unmodified.
Ed Wood is in the text.
Oh, the word.
Yeah.
Oh, I see.
And then, so we took, so they took a pre-trained base model and then tuned it on the IMDb data set. And then they randomly added Ed Wood and some positive labels to some inputs when training. And so on backdoor, so on the backdoor model on the test data set for the main test, main task, it was able to achieve around 91% accuracy, which is the same as the non-backdoor model. But on the backdoor task, it was able to achieve around 98% accuracy, which is, as what I would say, a great success. Okay, so the previous mechanisms for preventing backdoor attacks don't really work against this type of backdoor. For instance, one type is image perturbations. So which will discover little perturbations in the image, which are the backdoors. However, this type of attack can simply train around that. Another way is Sentinel, which just basically searches the image and sees if the model is focusing on like a very specific region, which is what a backdoor model would do. However, we can also train around that by just implementing evasion loss that just diverts the model. So like, for instance, as you can see here, with the evasion loss, the model will not just focus on a specific pixel on like a specific region, which would alert Sentinel, but instead it will look over the whole entire model, the whole entire image and focus on that, which therefore won't alert this type of protection mechanism.
So how do we stop this? Well, certified robustness can provide partial protection, but it won't work for universal adversarial perturbations. So trusted computational graphs proposed by the writers of the paper can detect this type of attack since MGDA requires an extra forward pass.
Okay, and then some discussion points are, first of all, for instance, for the facial recognition, I found it really weird that they were using ResNet instead of something such as YOLO or faster RCNN, which is actually designed for object detection. So I was wondering if this type of this type of attack could even be applied to such a model.
They want to do it covert, right?
Covert, yeah, but then.
But I mean, object detection is not covert. I mean, it's designed to detect the
Yeah, but couldn't you like hypothetically, if you had a backdoor, it would only like put bounding boxes around.
Yeah, maybe, yeah.
Okay.
But I think their application is more of like, I have a machine that just counts people,
Mhm.
and I introduce this backdoor, then all of a sudden change the functionality to face identification. So
But
kind of like you repurpose the machine to do something else that you want,
Okay.
which is interesting.
Yeah, it is interesting, but like, if you only have 5 labels, then it can only count up to 5.
Yeah,
pixels,
exactly.
which
Yeah.
is kind of a bit of.
Yeah, very limited, sure.
And then, they also, for most of these evaluations, they only used either, just smallest ResNet 18, or just a simple CNN with like 2 layers or something like that. So, could this work for, larger models such as ResNet 50 or more models such as EnvisionNet? And what about using this, type of attack for self-supervised models or unsupervised models, such as GANs? Like, for instance, could you have a backdoor, and if the backdoor, the GAN would produce like a whole entirely different image? And what about using it in reinforcement learning? Because since reinforcement learning is being applied a lot to robotics, if you had a backdoor there, then you could just change like the whole entire way, say an arm on the assembly line could work or things like that. And that's it.
Sure, thank you so much. One slide that was important, I want to reemphasize on that one. Let me actually go back. Oh yeah, this one. So one thing that is happening, I didn't discuss it in the class, but maybe it's a good time to talk about it now, is so one thing that these guys showed that, and then also other authors show, is one thing you can do in order to mess up with the machine learning models is actually changing the code itself, changing the training code or changing the inference code. Okay, and the idea is that since most of these machine learning pipelines, as you're going to see actually in your project, is you basically load some libraries that actually has written the code for the training and testing and so on. So you very rarely use the code from scratch. You never like write your own training data code or inference data code and so on. So you just call an API from PyTorch or TensorFlow and so on. What the attacker can do is actually injecting malicious code inside those libraries, inside the actual official GitHub repo of those. And given the complexity of these codes these days, they're actually arguing that this is indeed possible. So what happens is basically when you're getting your code from these repositories, for example, the code that you're going to get for your project 2, the code itself from the beginning actually has this vulnerability with okay, so it has this backdoor. For example, this one specifically doesn't calculate the loss correctly, and this way they can actually manage to introduce their backdoor. Okay, so it's something that is happening. It's a new thing that is happening because more and more people are just blindly rely on available codes in the internet, and they use it for their systems, and that could be potentially dangerous. So for production level codes, you have to be very careful of using other people's code. Yeah.
So it's technically a bug, but you're saying it could be used.
It's not a bug. It's actually the adversary actively inject this malicious code inside the repo. So think about this GitHub repo that everybody can contribute in this class, and one person actually injects some malicious code into that.
The branch is only committed into the public branch.
But at some point, these large systems, there are lots of different developers. There are some tests, as this also paper says, there are some tests that kind of like try to make sure that there is nothing fishy about the new part of the development. But it can easily, you can hide it as well if you can. So that's the idea, that you potentially you can like actually inject something malicious into the entire chain of your code. Does that make sense? All right, let's have a quick break and then we go to the third. Who is third? Okay, let's have a like 5 minutes break and then we can start this. All right, let's go. So let's continue with the third presentation.
Okay, hi, so today we're going to be presenting on update leaks, data set inference and reconstruction attacks in online learning. Now,
Also like the thank you. There.
okay, thank you. So kind of the context for this problem is that currently machine learning models are really popular, and one way to make them more robust and kind of up to date is to continuously update them. And then so machine learning models can be trained through online learning, which what that is as compared to static or like batch training, which is what we're usually used to. So with static batch training, what that does is we just have a fixed data set, we train the model, and then the model goes straight into production. It doesn't get updated or anything. But with online learning, what the model does is it takes in real-time input and then uses that input to change its weights or just basically be more flexible and update. And that's a kind of the updating side, just for terminology, is the data set that is being used to update the model. But what this means is that the model is non-deterministic. So for one input X, when I input it, I'll get a certain Y. And then say if I input the same X 2 weeks later, I could get Y prime. And so kind of the big question is, can these changes in the results reveal information about the updating set? And so unfortunately it can, and that's where our attacks come from. So kind of another terminology is posterior difference. And posterior difference is the difference in the results of the target ML's outputs. So kind of like what we can do is we can use a probing set, which is a fixed set of random data sets to probe the model and then get different results for the same input. And so I'll go into this a little more, but the model for the attack that the attacker uses is an encoder decoder model. And what the encoder does is it takes the posterior differences as inputs. It encodes into a certain value from which the decoder then decodes that value. And then from it, it can extract information about the updating set. And so the big problem with this is basically information leakage about both the model and the updating set. And then so kind of like what this paper focuses on is it focuses on 4 different types of attacks, which is a cross product between the kind of attack as well as the sample. So for all 4 attacks, we only use one updating sample, or sorry, one updating set, but with single sample, it's like we use with one specific data point from that sample, we're able to either reconstruct the model or sorry, not reconstruct the model. We're either able to reconstruct the data set or kind of reconstruct the model and make the same inferences. With multi-sample, what we have is we are able to use multiple data points. So kind of the threat model that the attackers seem to use is kind of like the using as little information as possible. It's a black box model in which the attacker doesn't know anything about the model except for the structure of it. And how it gets the structure is it gets the structure through model hyperparameter stealing attacks, but that's not the focus of this paper. So some of the assumptions that we have is that we know the architecture of the target model. We have a local data set that has similar distributions to the training data set, and that's really important later on. And then as well as our updating set is different from the training set. So just kind of the general attack pipeline for all the 4 attacks that I've shown before follow this model, where we have the actual model M up there, and then we have an M prime, which is the updated model. And then so with the kind of like our probing set is we kind of just like, we query both models, or sorry, we query the first model and then we get an update. And then with that update, with the updated model, we also query that. Then from that, we get Y probe and Y prime probe, which is the two different outputs that I talked about earlier. And then we get the posterior difference, in which the posterior difference is just something like Y probe minus Y prime probe. And then from there, then it goes to the encoder, gets encoded into a vector, which is the compressed version of the data, and then subsequently decoded. So just really briefly, for those of us who don't know what an encoder decoder model is, that's basically another ML model. And what it does is it consists of an encoder, which is responsible for converting data into a very specific format. And then the decoder decodes that data and then is able to extract information from it. And kind of like at a very high level concept, it could be like playing Pictionary, where on one end of it, the person is given input and then they have to draw that picture. And then on the other end, the decoder gets that same picture, but then they have to realize what it is that picture is and then kind of get the clues from there. So then following this, in order to train the attacker model, we have to first obtain the training data. So since we don't have access to the actual target model, in order to get ground data, we have to train a shadow model. And the process for getting the shadow model is, so first in training the model, we need training data. And the training data consists entirely of the posterior differences that I mentioned earlier. And then, so kind of like we do have the architecture for our shadow model. And then what we want to do is with our local data set that the attacker has, which this is why it's really important that the local data set has similar properties to the actual training one, is because what we do is we split the D shadow data set into a training set and an updating set. And so with the training set, that trains model, and then with the updating set, with the model that we trained, that's how we're going to get multiple shadow models that we can then get the outputs from. So from the updating set, we further divide that into more updating sets, and it goes to M. M depends on the attacker domain. But so from each of those, then we can use these sets to query and then further update more shadow models. So at the bottom, I should say M, but at the bottom, what we're ultimately going to get is we're going to get M prime models. And then so in order to get the training data at the very end, is what we can do is we probe the shadow and the updated shadow models with dprobe to get all these posterior differences. And then these posterior differences are the training data. So kind of the two attacks that we're going to focus on are the reconstruction ones, because those are more interesting. And then so kind of the whole goal of the single updating samples is to be able to reconstruct the one sample that we use to update the model. And then so how they were able to accomplish this is they needed an ML model that was able to generate data samples in the complex space. So with the other inference one, we're only generating one output, which would be like what exactly, for instance, they use the MNIST data set, and it would be what is the number that was used to update the set. Whereas this one, we actually would need to encode the individual pixels of that. And then so in order to generate something in the complex space, what we needed was an autoencoder. And an autoencoder is just another word for an encoder decoder model that's really efficient. So basically the autoencoder's goal is to learn an efficient encoding for the data sample. And kind of like below are some of the details, but essentially the most important part is that we have the attack model from before, but that attack model is in order for the inference model. So the important part here is that after training the autoencoder, we get a new decoder that we substitute into the previous model. And then so by substituting that decoder model, we're able to get something that can decode data in the complex space.
So I'll be going over the next attack, which is the multi-sample reconstruction attack. And it's very similar to the previous attack, but it's a bit more complicated because the previous attack, like we only update the model with a single sample, but now we're updating the model with multiple samples. So we have to generate, and we want to generate all of the samples that it was used to update our model. So what we do is we use the same general attack pipeline that we explained before, but then instead of using the autoencoder as the decoder of the autoencoder as the decoder, we want to use something that's more complex so we can generate multiple samples. And what the authors of the paper propose is to rely on generative adversarial networks, and we will refer to them as GAN, which is able to generate multiple samples instead of just a single one. And the GAN consists of a pair of ML model, which is the generator and the discriminator. And the purpose of the generator is try to generate fake data that looks real, and the discriminator tries to discriminate between the fake data and the real data. And the end goal of the training of a GAN model is for the generator to generate data that the discriminator cannot distinguish between real and fake. So unfortunately, classical GANs aren't enough for our multi-sample reconstruction attack. And this is because for a classical GAN, the generator can only generate fake data that is of a single distribution. But what we want to do is we want to generate data from conditional distributions that are conditioned on the posterior difference. And this is because, like, for every update, the posterior difference is different. So we want to be able to generate data based on that. So what the paper proposed is that we want to use the conditional, like they proposed this new type of GAN, which is called the conditional best of any GANs. And we will refer to it as CBM GAN. And what it can do is that it can condition the generated samples of GAN on the posterior difference instead of just a single distribution. And then similar to the single sample attack, we take the generator of the CBM GAN and use it as a decoder in our attack model. So this is a diagram of how we use the generator of the CBM GAN as part of our general attack pipeline. So as you can see, our generator takes two input. It takes the latent vector, which is like an encoding of the posterior difference, and it also takes samples from the Gaussian distribution. So it samples based on random seeds, and then it uses the samples from the Gaussian noise and combined with the latent vector in order to generate samples that should be of the same distributions as the samples in our D-update set. So we want to generate so the number of samples we want to generate is the same as this number of samples in the D-update set. But what the authors propose is that we don't tell the generator, hey, let's generate the size of D-update samples. Like, what the authors propose is that we use the generator to generate a large amount of samples. And then we use k-means clustering to cluster these data into k clusters, k being the size of D-update. And once like we have these k clusters, we take the center of these clusters, and then we use the center of these k clusters as the samples we want in our D-update set. So in the end, we want to produce not exactly D-update, but as close to D-update as possible. So now we'll be going over how the paper evaluated all four of its attacks. So all of these attacks are evaluated using the MNIST, CFR10, and Insta NY data set. And this is because like the authors want to show that these attacks are robust to like all sorts of data. And this being like number recognition, CFR10 being like image recognition, and Insta NY is like, it's a data set about like different tags people in New York use on Instagram, and then it matches it to their location. So for the MNIST and CFR10 data set, the authors use the CNN to build the shadow and target model, and for Insta NY uses a multi-layer perception. So for all four attacks, the updated ML model is created with like one more extra epoch of training, and the performance is measured with MSE, which stands for mean square error, between the updating and reconstructed data. And then we compare the MSE, which is the performance of our attack, to baseline models, and the baseline models are different for the single and multi-sample. And these are images of what the MNIST and CFR10 data set looks like. And now these are the results of the attacks. As you can see, like the accuracy is very high, the MSE is pretty low for all sorts of data, but we think like it'll be easier for us to understand how well the attacks perform compared to the baseline models. So we'll be starting with single sample. So the orange is the MSE of the attack the paper proposed, the single sample reconstruction attack. And the blue is called an oracle, and oracle is which like is the lower bound to how well our proposed attack can perform, so that's a lower bound, and then the green and red are baseline models. And as you can see, we perform much better than most of the all of the baseline models, and then we perform like pretty close to the Oracle, which is supposedly the lower bound. And then for the multi-sample, there's also a lower bound, which is a 1-to-1 match. And then the green and the red is the other baseline models, and even for multi-sample, we still perform very well compared to the other baseline.
So the lower is better, right?
Yes, lower is better. This is MSD. And I think, and here is the actual visualization of how our tag perform, which I think is the coolest part. So for the single sample, the first row is the actual data that is used to update the model that they train for MS. And then the second row is what the attack was able to generate. So it is the reconstructed data set. And then the third row is the Oracle, which is like the best our attack can perform. As you can see, like for the single sample, their reconstructed data set like pretty closely match the data that is used to update the model. So they can infer a lot of information on what sample is used to update. And then for the multi-sample on the left side, this is the set of data that is used to update the model. And on the right side is what the multi-sample reconstruction attack was able to come up with. And then here is the performance on the C410 data set. Although it's not as clear as the MNIST data set, but there's still like a lot of information that can be inferred. So on the left side, it is the actual image that is used to update the C410 model. And on the right side is the top 5 best performing reconstructed samples. So they basically overlay all the samples that the CVM GAN generator generates, and they compare it to the actual image, and these are the closest ones based on MSC. So I think like some of these are still pretty good. Like for the horse one, can still sort of see it's some sort of animal that is used to update the set. And then some of our thoughts after reading this paper is like we think these attacks they're actually able to extract information, and online learning is actually used in a lot of places as we will always get more data and we want more data to improve our model. So we think that like when people are using ML model that they don't want data leaks, like they should consider defending against these types of attack, as the privacy of the data can easily be, not easily, but it's possible that it can be leaked to the public based on this type of attack. So some of the future work include, like the paper didn't really cover how they plan on defending against these 4 types of attack. So future work is like an in-depth exploration of effective defense mechanisms against the 4 attacks. And then another future work is when we constructed the probing set, which is the set of data that is used to query the model before it was updated and after it was updated, what the authors did is they just pick a random set of data. But then the author says there might be a way where we can choose these probing set more carefully, which can reveal more information about the model. And some of the discussion points we came up with is how can we defend against these type of attacks? And then like, do we think the assumptions of the attacks are realistic? Because it assumes like we have data of the same distribution as the data set that is used to train the model, which we're not sure if that's possible in all sorts of scenarios in the real world. And the last question we thought of is, are there other ways to carry out this attack without a reliance on a shadow model? Because it also assumes that we're able to steal the architecture of the model that we want to extract information out of. And that is it.
Thank you. This is a tough paper. Good job on describing it very well. One thing, I'm not sure if the authors mentioned this, if you go back, so part of the, the discussion points.
Oh.
Yeah, so I mean, part of this that can be more realistic is usually this online learning models are distributed. So for example, Google use online learning for keyboards and keyboards in there, what you're typing. So almost all the Android devices these days have this. And the idea that this can be realistic is that now one of these devices becomes an adversarial device, an adversary. in that case, they have access to the same, almost the same distribution,
I
because
see.
they are one of the, generators of data, so they probably have access to the same data distribution. And they also have probably access to the model itself, because again, they are one of the users. So the scenario in which this becomes more and more realistic and more possible is when you have a distributed system that one of these players in this distributed game becomes an adversary. And all of these things now become a realistic assumption. But yeah, that's very valid. Any question, guys?
You showed like a work code that was 5, but then like the average one was 8, and the original was 8. We said orcos like, or in the next slide. You said the orcos like the best. The second, so on the top of the page, right?
Oh, for this one?
Yeah.
Yeah, the bottom is the oracle, which like the paper described as, it's like a lower bound to how it can perform. So basically how the oracle works is like, as we mentioned in the single sample, we create an autoencoder, and it basically just passes like the aid that is used to update the image through the autodecoder, which like encodes it into like some kind of compressed data, and then it decodes it. So I guess like this just, the autoencoder just happens to like encode the aid into like more
Yeah.
similar to a
The
file.
autoencoder itself is not perfect.
Yeah, because it's
So-
from compressed data and it has to like recreate the actual.
It's just on average has the best performance as far as I understand. Because it's just literally get the input and then do the output. Versus the second one is that you have to create the data yourself and then it goes through the output. So like an additional step needs to be taken. But generally the autoencoder itself is not the best way of doing this. So it's not ideal, but in their setup, that's the best you can do. All right. Thank you, guys. Thank you. So guys, you're missing part of the lecture, those of you watching the video. But maybe at the end of the class, I'll record a separate part. But what we're discussing now is how the out of order execution works and how this can be used for transient execution attacks. What I'm showing here is that you can run things out of order and then you get the performance benefit off of that. But the biggest problem would be branches. Okay. So in branches, what we have, as I'm showing here, is that in memory we have a flat, sequence of instructions. So for example, we have the code block A here. We maybe put C afterwards, the else part, and then we put the block B after C, and then we put block B after B. So if the branch is taken, then we have to run A. Then we have to jump over C and then run B and then go through the D, right? On the other hand, if the branch is false, we have to do A, then continue with C, but then we have to jump over B and then go to C, right? So one of these two different options. So at some points, we need to skip some of the instructions. And if you go back to the example that I was showing here, I1 to I9, there is some cases that you maybe have to skip some of these instructions and then maybe run this, and this, right? And in some other cases, you have to run these 5 and then skip over some of these and then continue, right? So that's the problem with the branches. And if you want to run things out of order, that could be challenging. Okay, so how do we fix the issue of the branches? One option is that you can stall the processor, which means that whenever you reach to the branch, you stop doing out of order execution. You just normally run your things as you do before. So you just run instructions one by one, okay? And that could resolve the issue. But that means that, again, we are going back to that underutilization issue, that we cannot run all the instructions. We cannot fill the processors with all the 4 issue or 8 issue or whatever we have. So that's not a good fix, because as we're going to show, generally in modern systems, branches to resolve the outcome of the branch, to know whether this branch is taken or not taken, it usually takes a lot of cycles, somewhere between 2 to 8 cycles, depending on the design, which means that we have to wait for 8 cycles for this branch to be resolved until we can actually continue doing out of order execution, okay? And if you have lots of branches, which actually in most programs we have around 20% of the program is usually branches, means that we are paying this penalty for more than 20% of our design, which is not great, okay? So what we are doing is we are using this thing called prediction or guessing. We are saying that, okay, we have 2 options, right? What we can do is just take a guess. We assume that whenever we reach to this point, this branch, we think that we either is true or false, whatever. It's just a random, we can make that decision randomly and start executing those instructions. And in case that you made a decision, you can always, you recover from that mistake and go back and execute the other one. But if in most cases you make a correct decision, then you don't have to do anything. You make a guess, you run things, it works, everybody is happy, right? So it's kind of like you completely eliminate the effect of branch by this guessing, especially if your guessing is correct most of the time. There's a whole bunch of how to make this guess and how to design the branch predictor, which we're not going to talk about. But the idea is that we are just, whenever we get to the branch, we make a guess, and this guess in most cases is like 90%, more than 90% correct. So in 90% of the time, we don't even notice that there is a branch. In only 10% of the time, we're gonna see that, oh, we made a mistake, but there is a mechanism to actually recovering this mistake and going back and running this second issue. All right. So this strategy is called a speculation. Okay. Branch prediction is one example of a speculation. It's not just the only speculation that we use in modern processors, but speculation is generally this process of guessing and a potential outcome in order to improve the performance of the system. And branch, when we are reaching to the branch and guess that, okay, this branch is going to be taken, although we don't know the actual answer, is part of the speculation. And then when we are running things during when we are reaching to the branch, the last thing before I let you go, we don't know the answer that whether this branch is taken or not taken. Let's say that we take the guess and think that this branch is taken. We start running things, and at some point we're going to get the answer about that whether this branch is taken or not taken. This window is usually called the speculation window. We still don't know whether we have made a correct decision or not, but we continue running and executing instructions. So this is the window that we call speculation window. And during this window, we are basically just run instructions, but we might or may not use it in future, okay? And then, as I said, if we, at this point, we figure out that we made the wrong decision, we just flush all of these things. So we basically say that, okay, whatever we did from this point to this point, I just discard all the changes from this point, and then I'll just continue with the correct path, okay? I mean, the way that we're doing this, it's not important. We use what's called an ROB or reorder buffer. I'll probably just describe this in the next slide. But this would be the way that we actually design this attack. I'm going to describe the attacks at the beginning of the next lecture, and then we're going to move on to the second part of the side channel, which is the physical side. Thank you. Yep.